All right, so in this video, we're going to talk about the dot product. And I've gone ahead and defined two vectors, v and w. You'll notice they're both in R2. You can actually dot vectors of any size, provided the two vectors you're dotting are actually the same size. So you can dot two vectors in R3, R4, R5, wherever. You would just need to expand this process. And it's a very simple process. We'll go ahead and say that if we want to dot v and w, so v dot w, this is actually going to be now where we take the first component of v and multiply it with the first component of w. So v1, w1, and then plus, and do the same thing for the second components, v2 times w2. So v2 times w2. So that is the dot product of v and w in this case. And as I mentioned before, one of the biggest takeaways is that this result, the result of a dot product, if you look carefully, this is not a vector, this is a scalar. This will be just a constant that is a result of the dot product. Okay? Now, there's going to be a bunch of properties of the dot product that I want you guys to take a look at. They're on page 717, and many of them are very important. One of them in particular is that the dot product is commutative. So that's saying that if v dot w is going to be the same thing as w dot v. That is one in particular that's very important. Please know that. Please read those. Another one that is very important is number 4. So we're actually going to do a proof of number 4. And number 4 says that v dot v is going to be the magnitude of v squared. Okay? So for the proof, I'm going to start by saying let v equal v1, v2. Okay? That's me defining the vectors that I'm going to use. That's a very important part of the proof. Then from there, I'm essentially just going to work it out. So v dot v would then be v1, v2 dot v1, v2, and when you dot those, that gives you a v1 squared plus v2 squared. So when I multiply v1 and v1, I get v1 squared plus, then v2 would be v2 squared, which we know is going to be the magnitude of v. So if this had a square root on it right here, if it had a square root on it, that would be the magnitude of v. It doesn't, therefore it's got to be the magnitude of v squared. Okay, so again, a very, very simple proof, but one that I wanted to bring up to you because of an upcoming assignment that you guys are going to have where this property in particular comes into play. So again, please review page 717, those properties, and let's go ahead and move on. All right, so one of the applications of the dot product is to help us figure out the angle between vectors. So if I've got a vector here, I've got a vector here, maybe we'll call this one v, maybe we'll call this one w. The angle between the two vectors is going to be found using cosine theta equals v dot w divided by magnitude of v times magnitude of w. Okay, and so of course, as you would work this, your theta would then equal the inverse cosine of that whole thing. The reason I mention that is because technically there's two different angles between vectors. You've got the one I've marked, and you've also got this one here. Using this approach for inverse cosine, knowing that inverse cosine is only defined in quadrants 1 and 2, this would then tell us that our theta is going to be between 0 and pi, and that's why we're going to get that angle that I have marked. Now, before moving on to an example, I do want to point out an observation here real quick. We've already talked about the idea that two vectors are parallel when they're scalar multiples of each other. Okay, that's important to know. That's the way that I want you guys to determine if two vectors are parallel, if they're scalar multiples of each other. To determine if two vectors are perpendicular, we're going to observe that v dot w is going to equal 0, implies that our theta is pi over 2. Okay, now let's think about that. We know that if the cosine theta part, if that whole thing equals 0, that's because this theta was pi over 2. right? Pi over 2 is going to give us a perpendicular angle. Well, when it comes to looking at this, and this being true, if I multiply off this bottom, what I have left is the idea that v dot w equals 0. So anytime you have two vectors and you dot them, if the dot product of two vectors is 0, then those two vectors are perpendicular. Okay, that's going to be the way that I want you to determine if two vectors are perpendicular. So we've talked about parallel and how to decide, and we've talked about perpendicular, how to decide. Neither of which requires you, nor should you, go through this entire process to determine if it's parallel or perpendicular. Okay, I do want to take an example though, or take a look at an example where we do find an angle between two vectors. So I'm going to go ahead and clear the screen, and we'll look at that. All right, so we'll take a look at the example I have up on the screen. We've got vector v and vector w. If you'll notice, I've written this in the linear combination form, and the first thing I would do in this particular problem is actually write it in its component form. So for the first one, we've got a -1 out in front of the I, we've got a 1 in front of the j, and then you can see we're actually in R3 because this guy involves a k, and we're going to need to be in the same dimension here when we dot these things. So we've got a 0 right there. And then our w would be 0, -1, 1. All right, so cosine of theta is going to be v dot w. So the dot product would be a -1 times 0 plus 1 times -1 plus 0 times 1. Okay, so -1 times 0 plus 1 times -1 plus 0 times 1 right there. And then in the denominator, we're going to have two square roots. We're going to have -1 squared plus 1 squared plus 0 squared. And then we'll have 0 squared plus -1 squared plus 1 squared. So this would be the magnitude of this guy, and this is the magnitude of this guy, each of those squared. All right, so cleaning that up, we get cosine theta equals -1 over. This will be a square root of 2, and this will be a square root of 2. So that's going to be a -1 over 2. And in which case, cosine equaling -1/2 tells us that theta is going to be 2 pi over 3. So the angle between these two vectors is going to be 2 pi over 3. So a pretty straightforward process. And again, you will prove that formula in an upcoming assignment, so you'll have some justification on why it works the way it does. Okay, so now we're ready to talk about vector projection. Now there's two parts to this, and both of which are going to be very important for a variety of things, but one of them is going to be a scalar, one of them is actually going to be a vector, so we'll distinguish between those as we go. Now, in terms of the vector projection, what this is for us, in this particular case, we're going to be looking for the projection, PROJ for projection, of vector A onto vector B. So this almost looks like it's written like a logarithm with a base, but it says the projection of A onto B. Projection of A onto B. The projection of A onto B is going to be this vector right here. It's like if you look at this from above, if you look at it from above, this vector is going to look like it's laying right here. Okay, and so that's going to be our projection vector. And so clearly the way that came about was from coming straight down from where the vector A, the terminal point on that vector A. All right, so I'm going to call that theta, and let's suppose we're searching for, or we'll call this guy question mark. Let's suppose we want to know what that is. Well, we know that cosine of theta is going to be the question mark over, not vector A, but the magnitude of A. We have to quantify the vector, so we take the magnitude of it, which means that question mark is going to be magnitude of A cosine theta. Okay? So that's important. That's really, really important, because this is what we're going to call the scalar component. So the scalar component. So this guy right here, I'm going to come back and change now. This is the magnitude of A cosine of theta. All right. So now, in terms of the actual vector itself, what we're going to do is we're actually going to normalize b. We're going to bring b back to its length of 1, and then we're going to multiply it by the length, the scalar component. So I'll take my scalar component, and I'm going to multiply it by b having been normalized. So that's going to be 1 over the magnitude of b times vector b. Now I'm going to simplify this a little bit, actually quite a bit, by getting rid of the cosine. We know that cosine from earlier has a big formula that it's equated to. So I'm going to take my magnitude a, and then I'm going to have my a dot b divided by magnitude a, magnitude b, times 1 over magnitude b times that b vector. And so it looks like the magnitude of a's can go away. And when all said and done here with this, what I have is an a dot b divided by magnitude of b squared times vector b. And if you'll pay close attention, notice a dot product is a scalar, a magnitude squared is a scalar. This is a scalar being distributed into a vector, the result being a vector. That vector that we're talking about is this guy here. So this guy here is the projection of A onto B. Okay, so as you work through the homework, as you look at some of these problems, it's important to understand what's really happening here. All we're doing is normalizing B, that's me normalizing B, and then multiplying it by the appropriate length. That length was magnitude A cosine, as we found, and I just used our dot product angle between vectors formula as a substitution for cosine. Therefore, we don't really even need to know anything about theta. All we need to know is our A's and B's. All right, so we'll take a look at an example here. We've got vector A, we've got vector B, and I've broken this apart into 2 questions so that I can better clarify the distinction between the scalar and the vector itself. So the scalar component and then the projection of A onto B. The scalar component, if you remember from the previous screen, that's the magnitude of A cosine theta, where that cosine was A dot B divided by magnitude A magnitude B, and in this particular case that goes away, leaving us with just A dot B over magnitude of B. So then when I dot those 2 vectors, that's going to give me let's see, a 4 plus a 20 minus 11. So when I dot it, I have my 4, my 2 times 10 is 20, and then my 1 and negative 11 will be negative 11, and then the magnitude of B, that would be, let's see here, 4, 100, 121. So I have a 4 plus 100 plus a 121 under that. So that's going to give me a 13 on top. On bottom, that's going to be the square root of 225, which is 15. So the scalar component here is 13 over 15. Now, I've got that part done. Therefore, for the actual projection, remember that's just going to be the scalar times the normalized vector for vector B. So I just need to normalize vector B. So that's going to be a 1 over, and we've already done that. That's going to be the 15, 2, 10, negative 11. And so that's going to be 2 over 15. And then we have a 2 over 3 when I simplify. Then a negative 11 over 15. So my final step then is to take the 13 over 15, multiply it in there. Remember, right now I just have my vector B that's been normalized with a length 1, but I want it to have a length of 13 over 15. So then my final answer then when I distribute would be 26 over 225, 26 over 45 when simplified, and then negative 143 over 225. So that would be the actual projection of A onto B, the correct vector for that. So I thought this was a good problem in order to better understand the scalar part versus the actual vector part. If you're not asked to do this, then you can certainly just combine it all into the formula we set up for the projection vector in the previous slide. But in this case, we split it up so that you could see it better.